Thanks all for coming for this talk, which is about Ceph RADOS block device, or RBD as we all call it. Okay, so I am Venky. I'm a Ceph developer working at Red Hat. Okay now? Yeah. So I'm Venky. I'm a Ceph developer working at Red Hat. I started as a cluster developer, when cluster was still cluster. And then I moved into Ceph last year, and it has been a nice journey. Okay, so what is Ceph? Ceph is a software-defined distributed storage, massively or mostly ultra-scalable software-defined distributed storage. All components in Ceph scale horizontally. There is no single point of failure as such. All components are designed in such a way that, if nodes or components fail, which typically happens on a distributed storage, the cluster is still up and operational. Ceph is self-managing and self-healing. We'll talk about this in some detail. Since this is about librd, we won't go into more details how replication is done, but at a high level, Ceph is self-managing and self-replicating and healing. So if your nodes go down and come back up, you don't have to do any administrative task or less administrative tasks to get your cluster back up, up with a healthy status. Louder? I need to be able to. Okay. Okay, so Ceph runs on commodity hardware. There's no vendor lock-in. It's open source. It's great. You can have a bunch of x86/AMD boxes, prepare a cluster out of them, and have Ceph up and running. Also, Ceph is all object, block, and file. Traditionally, Ceph is an object-based distributed storage. We build object, block, and file on top of it. Okay, so here I put down the various Ceph components. At the lowest level is RADOS, which is stands for Reliable Autonomous Distributed Object Store. This is the part which handles replication, self-healing, self-managing, and things like that. This is the part what we are not talking about today. We are talking about block, which is all three things, which is object, block, and file, are built over something called as librados. RADOS provides an API in the form of a library which is called librados, and all three, RGW, RBD, Ceph FS, use librados to interact with the Ceph cluster. RGW is a web services gateway for object storage compatible with S3 and Swift. RBD, which we are going to talk about in detail, is a fully distributed block device with integration with OpenStack and CloudStack. Ceph FS is a distributed POSIX compatible file system. Okay, so we are talking about RBD, which is RADOS block device. RADOS block device is, you can access the block device, which is like a distributed behind the scenes. What you see is just a block device in the form of either a library in the form of librd, which is built on top of RADOS, or it's also available as a kernel module in the form of rbd.ko, which you can mod probe into your kernel and get things like dev rbd0, dev rbd1, map rbd images to your host, and accesses like a typical block device. You can make a file system on top of it, put your standard Unix tools, and behind the scenes, it's just distributing all your data in the RADOS cluster. So as you see here, the RADOS cluster, you have different components labeled. What you see as these black boxes, which are labeled as M, are monitor clusters. RADOS needs a small operating cluster to hold its own metadata. You can think it of as different maps which RADOS needs to kind of operate correctly. So monitors is a small cluster that holds these maps, and that's the main thing that you need to get or put or do operation in a RADOS cluster. The other boxes which you see, which are like these directory trees, directory hierarchies, are something which is not really required for object and block. These are actually metadata servers, or MDSs as we call them. They are required only for the Ceph file system. And what's stored in MDSs is the actual directory hierarchy. Okay, so MDSs are, there's not a single MDS box, it's an MDS cluster. Okay, so the directory is partitioned along all these MDS clusters. And the others, what you see, these other boxes are the OSD nodes, or the object storage daemon nodes. These are the nodes or services which actually hold your object data. And as I said, LibRados provides API, which we'll go into some detail into that. LibRados provides APIs to interact with the Ceph cluster. On top of that, we developed LibRBD, which will give you a view of a block device, which is backed by the RADOS cluster. That's the user space part. The kernel space part is the KRBD, or the kernel RBD, which uses libceph, which is fully into the kernel, that knows how to talk with the monitor and the RADOS cluster. Yeah.
See here, so you distinguish between node and storage, but confuse the both. What is node? What are the boxes?
Boxes, you can see, these M's are actually, what you see, these black boxes, they are monitor nodes. Okay, there is no restriction that you have to have a different monitor cluster. Well, that's the preferred thing, but they can coexist with other roles like OSDs. But in a production cluster, they are preferred to be on a separate node. And that stands true for anything else. The OSDs, there's no restriction that there has to be one OSD per node. There can be multiple OSDs per node, but they need to have different drives for, for performance purposes. But any of them, we can operate Ceph on laptop. So it's like one single node. The MDSs, the monitors, and the OSDs, they all reside on one node. Okay, but if you're taking it to production, you need to really plan for. Monitors are small. Okay, they just do maps. They just replicate maps. They run Paxos, but they replicate just maps, and they need to be very small. Okay, so they don't need to be a very powerful set of boxes. OSDs, yes, they need to have good memory, CPU capabilities, and if possible, SSDs or NVMEs. Although that's not required, but if you're doing real, if you're putting petabytes of data onto your cluster, it's good to have SSDs in your OSDs.
So each OSD is considered a node?
Each OSD is a service. You can think it as a daemon that's running in that node. Okay, you can have multiple OSD daemons running in that node. Okay.
So users are provided what? OSDs?
Users are provided with a configuration file. I'll come to that. Configuration file which says, this is my endpoint of the monitor. They go to the monitor. I mean, this is all encapsulated in LibRados. So you generally use a library or LibRBD. And you provide it a conf file which says, this is my monitor. The monitor has the truthful information of what's where. Okay, so once you reach the monitor knows where are the OSDs. And once you know that, you know the topology of the entire cluster. Okay, so a bit about LibRados. LibRados provides an API of doing transactions around a single object. Well, I say single object because that's what normally we do in Ceph. There have been contributions in the form of patches to do a transaction on multiple objects, but since objects are randomly distributed across a cluster, doing transactions for multiple objects is hard, so I didn't mention it here, but that state is still ongoing. LibRados provides a rich object API. We all know object APIs put, get, delete, but it provides much more than that. You can do partial overrides, read, set attrs on it, so it's much more capable. The partial overrides and reads make LibRBD pretty easy. Okay, and what we can do is have compound atomic operations per object. So what I can do is if I have an object in my cluster, I can say, I can have a compound operation which says if read this attr, if that attr matches some predefined value, do this right and set this attr again. So set a different attribute. So all these three operations are one compound and it's atomic. So it's either all or none. That's the guarantee that LibRaDOS provides us. Yep. Yeah, transactions. So for that, we have a write-ahead log journal. That's why I said SSDs, because once you're trying to, these OSD daemons, the OSD does the operation on the backend file store. For that, they need a write-ahead log. That's normally that write-ahead log, you will plan to put it in a journal. Right? So once it's committed in the journal, it's safe. You can act back and later replay it on your file store. And what RADOS provides more is like RADOS classes. These are like stored procedures from the database world, but it's not really stored procedures. It's like tiny bit of code which can run on the server, on the OSDs, which knows how to understand a typical data format. You can pass that data format from the client, and only that will know about it. So you can execute a stored procedure in the form of RADOS classes in the server. Okay, now let's go more into what RBD is. RBD, as I told, this is more about librd. Kernel RBD, I don't cover much. I just have one slide on it. It's mostly librd. But I do point out the differences in all manners in performance and capabilities. Okay, what does RBD give us? RBD gives us a block device. Behind the scenes, it's actually striped. The image is actually broken down and striped across the entire cluster. So what you see with RBD is, say, a 10 gigabyte image that's actually broken down into different chunks, and these different chunks are placed by something called as crush that's done by LibRaDOS. So no one single OSD is responsible for your entire image. It's responsible for some part of the image in the form of chunks. RBD images are thin provisioned. So once you create a 10 gig RBD image, you have absolutely no data in your cluster. You just have a bunch of metadatas, which is required. That's very small, but absolutely no data. As you fill up your image, the objects are created, and then your size is filled up. And RBD provides read-only snapshots and copy and write clones. This is the feature that makes it extremely useful for cloud deployments. It's one of the main storage, choice of storage for OpenStack. It's funny that someone yesterday didn't mention about Ceph at all in the OpenStack talk. I find it very funny, but it's like it's the choice of storage for OpenStack. You have snapshots and copy and write. So with snapshots, what you can do is you have say your image on your in your virtual block device. You can take snapshots, and that's the point-in-time view of your image. And yep. That's done by RADOS. So the question was whether the image is replicated. The image is broken down into chunks. Each chunk is actually replicated. So that's the part which is handled by RADOS. RADOS has something called as pools. You can have different pools for my object store, my RGW, my file system, and my block device. Each pools you can choose a replication factor. Normally it's 3, because that's what you at least want, minimum of 3. And each chunk of the image is actually replicated thrice.
So when the snapshot is taken,
yeah.
So will the replicated copies also be, we take at a point in time snapshot of the complete state. So will the replication, objects that we have, will they also be part of that particular snapshot?
I'll come to that. You're pretty fast.
Okay, cool.
I have that in slide 10. I'll come to that too.
Not have snapshot on writes. It has only read-only snapshots. You want
snapshots are read-only.
Active as well.
That is one. You mean writable snapshots? There is something in that. I'm not really sure. I have it mentioned on my slides. That's the part I was scared about because I didn't know about it much. So I'll come to that. Thanks. So we have read-only snapshots, and you can have a number of clones out of it, take in any number of snapshots. Also, we have image features. You can create images with different capabilities. I just mentioned 2 of them, but we have a bunch. These capabilities allow you to do different things. We'll come to this later. And as said about the integration part, we have good integration with QEMU libbert, as I said, with the OpenStack model. We have the Linux kernel integration in the form of RADOS block device. That's a block device driver in the Linux kernel. And images, we traditionally had 2 format of images, V1 and V2. V1 is deprecated. V2 is the choice now because it supports all these fancy features. Okay, so when you create a RBD image, as I said, it's thinly provisioned, so there is absolutely no data initially. What you have is a bunch of metadatas. Internally, librd works with image ID. So you give it a name, say you give R0, R1 your image names. We generate a unique image ID from it, and that's what is usually operated on. The good thing about that is if you happen to rename your images, it doesn't affect anything because the ID remains the same. So these here I put forward, some image metadata objects. All of these are objects which are stored in your RADOS cluster and replicated. So you normally work with image name. So we have this. So we want to internally we work with image IDs. So when you provide a image name to a librd API, say you want to do write or whatever, open an image, provide an image name that's converted into an image ID by looking up, the rbd.id. The image name object that stores the image ID. Then we have a header object. This is an important one because many things are done with the header object. All the locking is orchestrated by the header object. The header object internally has, as an attribute, we store the features. Features, as I said, these things like lock and fast saves and others. All of these are attributes in the RBD header image, the number of snaps you're taking, the current snap ID, and things like that. Then we have another special object called RBD directory. This is to speed up the listing of RBD images. So if you create, say, 1,000 images, we don't want to do a scan of the entire RADOS cluster of your pool and then list out images. What we do is we have a map of what's the name to ID. These are stored as attributes for the RBD directory object, and we look that up, and that's how you get the listing. RBD children, this is the interesting part. Yep.
Do we use any key value data?
Yeah, we do. We use level DB.
Okay.
Yeah. So if your key value attributes are small, we just directly put them in an extended attribute. If they are big, they just fork out to the key value store instance. Level DB is what's used. And this special object, which is the RBD children, is actually what maps and clone. When you actually take a snapshot and clone, the clone needs to kind of reference its parent for various reasons, which I cover later. So those details go into the attributes of the RBD children object. Okay, so where's your data? Your data is also, as I said, striped across the cluster. It's thin provision, so you start with absolutely non-existent data, and then you have this. Your object name, which is your data, is in the format of RBD data. You have the image ID dot the. We use numbers, so give the number. The RBD, the object name is actually generated from the offset you write into the image. Okay, so say you have a 4K chunk size. Anything between 0 and 4K minus 1 would go into the first object, and you can do the math. Objects are sparse, so since RADOS provides us to write partial data and read partial data, objects, at least in the case of librd, are never fully occupied. They might be sparse, and mostly are. Snapshots capabilities are handled by librados partly. The snapshotting is done by librados, but the clone copy on write is done by librd. We'll cover this. This is a typical RBD image info, which you will see. I just created a 10 gig RBD image called R0. You can see different things. This is the ID I was talking about. Format 2, I have features like these, layering exclusive block. I'll explain these features in some detail later. Yep. Yeah. There is some, yeah, as of now, yes, but as we go later, we are actually changing our file store. You won't see them as files. I'll cover that. I have a hidden slide for that, so if people are interested, I'll show you. That's after the Q&A slide. Okay, striping. Uniformly, we have all the objects are uniformly sized, but they are sparse. We default to 4 megabyte object size. Objects, as I said, are randomly distributed across the OSDs in the pool. It's handled by an algorithm called data distribution algorithm called CRUSH, controlled replication and scalable hashing. Once you chunkify your image and put all the objects in different nodes, you can do parallel IOs. It's not one big file that's sitting on the file system. So your IO workloads are spread across the cluster, and no one single node is responsible for the entire image. Yeah, so we have, yeah.
As you, what happens to the existing object?
That's handled by CRUSH. So the good thing about CRUSH is it takes care of migrating as less as possible. Okay, but that depends on your topology, how you have. So there's something called as a CRUSH map, which you initially feed it to the RADOS, LibRaDOS. LibRaDOS understands CRUSH map. So you can say these 2 OSDs are in rack A. These 3 OSDs are in rack B, and this is in a different, this has a different power supply by itself. CRUSH will take this map, take your image name. It knows the replication factor. Each racks will have a different power supply and things like that. Tunables, for striping, we have just 2 tunables, stripe unit and stripe count. The default stripe unit is 4 megabytes with a default stripe count of as 1. You can change that. It's called fancy striping. You can change to adapt to your workloads. If you have a small file workload, you can change stripe unit to say 4K and stripe count to 4. Yep. No, monitors. Monitors holds maps. There is something called a cluster map. Cluster map has mon map, OSD map, PG map, and CRUSH map. Monitors. That is a small cluster by itself that runs Paxos. Well, initially it has to get the map. The map divs. So you may add. Sorry for that. So you may add nodes or remove, or you may add OSDs or remove OSDs. Your CRUSH map will change. But every time it doesn't have to go to the monitors. Monitors hold the truth information, but the maps are lazily propagated across the cluster. All maps are timestamped by epoch numbers. Okay, so if you're in, say, epoch number E, say a client has an outdated CRUSH map of epoch number E. It contacts an OSD which has a higher epoch number. Okay, so the client gets to know that it has outdated map, and and it will get the refreshed map from that particular entity. Right, so it's lazily propagated across the whole cluster. Every entity in the cluster has maps. So the clients know about it, the OSDs know about it, the monitors surely know about it. That's how it's done. So you may contact any node, you may contact an OSD saying do this particular operation on this object. If the OSD finds out you have an outdated map, it replies back saying that your map is outdated, go and refresh your map. So you don't have to proactively go and poll or contact every single entity in the cluster. Yes, it stores the configuration. It has the truthful configuration because you need at least one entity to kind of contact. Yeah, for the bootstrap phase. And then you kind of lazily propagate and understand how the cluster has changed and adjust accordingly. Yes. CRUSH map, yes, because LibRaDOS, it's a part of LibRaDOS. LibRaDOS understands CRUSH map. So if you are using LibRaDOS, you don't have to do anything special on top of it. So in LibRBD, we don't really do all this map thing. We just use the LibRaDOS APIs, which takes care of that. So if you are doing an operation on an object which which has, say, the OSD for that object has vanished. When it tries to contact the OSD, it's obviously not there, so it'll go and check the monitors for the updated map. Stripe count and stripe unit allows us to change how to adapt to different workloads. If you have a small file workload, change it, put it to a lower value so that when you do copy and write operations for clones, it's quick. Stripe is how you chunkify your image. So your image might be 10 gigabytes. Chunk size. A chunk, which is an object, lives in the RADOS cluster. Depending on the pool size, it's replicated that many times on different OSDs. What do you mean by contiguous? Yeah, so 0 to 4 MB minus 1 is the first chunk, and things like that. So it lives on one OSD, but it's replicated to other OSDs. No, that 4 is on just one big file. Yep. Yeah. No, when you create an image, you can say I want the fancy striping, which is in the form of a striping B2 feature bit. You can say don't use the defaults, use this. Okay, I'll cover the I/O path now pretty quickly because I think we are running out of time. Normally, you will put your VM on LibRaDOS, LibRBD virtual block device. So your LibRBD is actually a part of your virtual machine and handle all the I/Os by the virtual machine. So this is what happens. LibRBD sits as part of the hypervisor, has its own cache, and talks to the RADOS cluster. All I/O that is done by the virtual machine goes to LibRBD. The virtual machine has its own page cache because it's normally running a kernel. So there's caching there. Once that cache is done, it comes down to the hypervisor, to LibRBD. And there's caching there too in the form of a LibRBD cache, which is enabled. So it's pretty simple. A VM would do operation on a particular offset or whatever, block offset. And that's converted to the object number by a LibRBD, depending on the stripe unit and the stripe count. And we do direct operations on that object. The cache is a bit tricky because it's a write-back cache generally, but historically there's a tunable which says start as a write-through cache, and once you receive a flush, move into the write-back mode. This is for historical reasons, for if you're running a virtual machine old enough which has barriers turned off. So if that's the case, and if you're still doing write-back, you might corrupt your image. So what we do is we start in write-through mode, okay. But as soon as we receive the first flush, which is a barrier operation from the guest, we change it to write-back. And it's pretty simple. Since LibRaDOS provides us with partial overriding of objects, what we have to do is just point to the correct object and do operations on it. So we come to the interesting parts. Well, it could be, but it need not. It could be, but recommended not to, because say if your OSDs are in different geographies and the primary OSD wants to replicate to the secondary, it has to go over the WAN, and that will, spike up your. Yeah, it's synchronous. Yeah, that is synchronous. Okay. So let's come to the interesting part, which is snapshots. The library provides a per image snapshot. RADOS itself provides pool level snapshots, but because you will have many library images in a single pool, you don't want to take snapshots of all your RBD images because you don't want it to be global per pool because you want to take for individual images. So RADOS library provides per image snapshots. The snapshots are itself handled by RADOS, but it does copy on write by itself. How that's done is whenever we do a lib-RADOS operation, a modify operation which in the form of a truncate or a write, lib-RADOS understands something called as a snapshot context, which is a list of snap IDs and the latest snap ID. When you pass this snapshot context, normally you generate this snap ID by consulting the monitor. Okay, I think that's there are some entities which just make up its own snap ID, but normally you will get it from the monitor, which is incremental. So you'll start with snap ID 2, 3, and incrementally go. You provide the snapshot context and the latest snap ID to a lib-RADOS that trickles down all the way to the OSDs for that particular object. OSD has enough information to know whether the object needs to be copied on write. If it has already done a copied on write because an earlier IO happened for that particular snapshot context, it won't do. It will just do that particular operation. But if it decides that that its own snap is logically older than the snapshot context you're providing, and it will do a copy on write, and then that's how it's done. So your history is actually preserved like that. So this is sent with every IO operation. When you do pool level snapshots, RADOS manages the snapshot because RADOS itself manages snap context. Because here library manages the snap context, we call it self-managed snapshots. Self-managed in the sense we don't do snapshots, we just store the snapshot context and provide it to RADOS whenever necessary. And once you have taken a snapshot, the way to refer your snapshot is image @ the snap name. There's pool / I haven't mentioned the pool here, but normally, yeah. Object level deduplication, I don't think so. I don't think so we got there. There were some PRs in GitHub, if you want to look it up, regarding compression, encryption on disk, but deduplication, there has been some discussion on the Ceph Devil mailing list, but I don't think so it made it to a PR. You can still check. Clones. Okay, so once you have created a snapshot, now you want to probably clone and get fresh images out of it. Clone is another, all of this is done by the RBD CLI. Okay, it's a very simple form of CLI. It's called RBD itself, so try it out. So clones, clones have copy on write at the object level. So the copy on write for clones is done by library itself. RADOS doesn't do it. RADOS does the snapshotting part and its own copy on write. When we try to access clone data is when library does copy on write itself. So what happens is when you clone a particular snapshot, the clone, what you get is a fresh RBD image. But that has reference to its parent because when you clone a snapshot, it's thin provisioned. You have absolutely no data. It just shares some data with its parent. Okay, so when you're when you clone a snapshot and try to do IO on it, the actual data is actually read from the parent. Okay, so if you recall the RBD children's directory, what we had, that had a mapping of the clones to its parent. So when we do IO on a clone, and if the object is not available, we can open the parent and read data from it. So copy on write is done by default. We have an optional tunable for copy on read. Normally, this is turned to, I'm out of time, so I have to rush through it. So copy on read is, when you're reading data, you will do copy on reads. So you'll read data from the parent, and that's normally done for a copy on write operation, but you will do it for a copy on read too. Clone, you can only clone a product with snapshot. That's because you can't delete a snapshot when a clone exists. That's because the reference will be lost and then you will have data losses. So you actually protect a snapshot before you can clone. But you can still do one operation which is called flattening a clone. Okay, so when you flatten a clone, you read all data from the parent and then write it to, you do a copy on read during flatten, and then you kind of disrupt the link so that now the snapshot and the clones are not related. Yeah. Copy and read, well, if you're doing small reads initially, you have, even if you do a 4K read, okay, you'll get the copy up is actually 4 MB. You do object size copy ups. And so initially if you're done random read here and there on a clone image, and after that, if you're planning to do a write, there's no copy up. So that will be, there's no performance impact of that. Okay, normally copy on read is turned off. It's for an extreme use case, I guess.
But if you have flagged
Yeah.
and then that clone, then you can take a snapshot of that.
Yeah, yeah. It's a normal RBD image. You can take a snapshot. You can clone it again, and things like that.
It becomes a new.
Sorry.
Once you flatten it,
Yeah.
it becomes a.
When you clone it, you get a new ID. It's like a new RBD image. It needs to have a new name, a distinct name, so it gets a new ID.
So it's no longer attached to the parent. That's what mentioned here.
No, once you flatten it.
Yeah.
Once
After
you flatten
flattening.
it, yeah. Once you flatten it, there is no association with the parent. You can unprotect it and delete the snapshot. And it can be, your clones can live in different pools and have a different feature set. Okay, I'm out of time.
Sorry.
I'll quickly do read and write and probably just do the KRBD part. Okay, read, as I said, what you need to do is when you do a read on a clone, if the object doesn't exist, we open the parent, read, and if the copy on read option is set, we do a copy on read, otherwise, we just leave it like that. As I said, the 4K read will turn into a 4 MB copy up. It's helpful for some workloads. Clones IO is much more interesting. What we do is we send an IO guard, which says if the object is not there, fail, but do a copy up. If the object already exists, you need not do anything, which means it was copy on write earlier. Also, there's one optimization where you can say, if you're doing an IO, which is like a full write, which is like the stripe unit size, okay, so there's no need to copy up again because you will anyway overwrite that object. Image features, there's a lot here, but I think I have to skip that, sorry. Kernel RBD, kernel RBD always, tries to catch up with librd in terms of features. We just got exclusive lock in the 4.11 kernel, so it's, journaling is not there and some other interesting features are not there, but, because kernel development is slow and hard, it will always try to catch up with librd. Librd is where we do the development first. Okay, RBD mirroring. In short, you have two Ceph clusters. You can asynchronously replicate your block device from site A to site B in a crash consistent fashion. I'll directly go to the picture. This is how it looks like. It's a pull model where you run the RBD mirror daemon on site B, and that pulls in changes from site A. You need an image feature called journaling. The RBD mirror feature make uses of that. The journal events are pulled from the remote cluster and applied to and those events are applied to the local cluster. Future, currently we just have one RBD mirror. We just support running one RBD mirror instance. So that's not horizontally scalable. We are moving to that. Currently in upstream master, we can run n of them, and one of them will replicate the images. If that goes down, the other takes over. So that's high available. Parallel image replication is work in progress, and other things are being worked upon. Okay, I can go into details, but I'm out of time. Sorry. Questions? Yeah.
Everyone must have the same stripe size as the parent?
Not necessary.
So it has a reference to the parent.
It just have reference to the parent ID.
Correct.
So when it has to fetch the first data,
So how do you manage different?
It has the reference to the parent ID. Given a parent ID, you can know its stripe unit, stripe count, and doing some math, you can know which object.
Internally you manage
Yeah.
that. Okay.
I explicitly mentioned it.
Okay.
Sorry. So meet me outside. You can. We have.
Corner outside.
Yeah, sure.
Corner outside, so whoever has questions can actually come in and we can have a seat there.
Thank you very much, and sorry.